Hello and welcome to the Maths Matrix. My name's Rebecca and in this VE Day special we'll be doing combinations. Combinations do come up a bit at GCSE on both foundation and higher tier papers, but they were also really important in the design and creation of the Enigma machine, which was used by Germans during the Second World War to send coded messages. We can't really do very much for VE Day at the moment in this country because we're all on lockdown, so I thought it would be fun to get all dressed up in vintage clothes and film a VE Day special of a maths video. I hope that seeing how simple GCSE principles can be extended all the way up to something as complex as the Enigma machine will be interesting for you. And I also think it might be a nice way to remember the work of all the brilliant mathematicians and engineers from both sides who worked really hard making and breaking codes during the wars. For this lesson, you'll need paper and a pen, and if you want to join in with the harder parts, then you'll need a calculator. First of all, let's cover the GCSE work. Sometimes on a foundation paper, you're told that two events are going to happen and you're asked to write down all the possible outcomes. So for example, you might be told that a coin is going to be flipped and at the same time a die is going to be rolled, and you might be asked to make a list of all the possible outcomes. This is actually really easy as long as you go in a logical order. So for the coin, we can have either a head or a tail. And for the die, we can have 1, 2, 3, 4, 5 or 6. That means that we could either get a head with a 1, a head with a 2, a head with a 3, a head with a 4, a 5 or a 6. Likewise, we could get a tail with a 1, a tail with a 2, a tail with a 3, tail 4, tail 5, and tail 6. So when they ask you to make a list of outcomes, that's all they want you to do. They just want you to list all the possible combinations of things that might happen. And rather than doing it randomly, just start with your first thing and match it up to each of those things that can happen, and then move on to your second thing and match it up to each of those that can happen. And then sometimes they might tie it in with a bit of probability. So they might say something like, what's the probability that you get a head and a 5? Well, altogether, there's 12 different things that can happen. So the probability of getting a head and a 5 would be just 1 out of 12, because there's only one item in that list of 12 that is a head and a 5. Another way they might give you a similar sort of question is they might say that in a restaurant, the starters are soup, melon, or prawns. And they might say that the mains are steak, fish, or quiche. And they might ask you to write down all the possible combinations of meals that someone could pick. Again, we'll just go in order. So you could have soup with steak, soup with fish, or soup with quiche. You could have melon with steak, melon with fish, or melon with quiche. And you could have prawns with steak, prawns with fish, or prawns with quiche. And so altogether we have 9 different combinations that someone could pick, and by doing them in a logical order we make sure that we don't miss any out. And then they might say something like, what's the probability that somebody chooses soup with fish? Well, there's 9 possible things and soup with fish is just one of them, so the probability of soup and fish would be 1 out of 9. They might say, what's the probability that somebody chooses quiche with any starter? Well, the probability that they choose quiche, there's 1, 2, 3 combinations that include quiche out of a possible 9, and that cancels down to a third. On a higher paper, they might also ask you about combinations, but they'll usually give you so many options that it wouldn't be realistic to make a list of them all. If we think about the previous example where there was soup, melon, prawns, meat, fish and quiche to choose from, altogether we had 9 possible combinations. So 3 starters and 3 mains generated 9 possible combinations. Now let's think of an example where 4 boys have to be partnered with 4 girls, and we'll call the boys Alex, Bertie, Chris and David, and we'll call the girls Alison, Bonnie, Claire and Dawn. Now, if we were to partner up the boys and the girls, then Alex could be put with either Alison, he could be put with Bonnie, he could be put with Claire, or he could be put with Dawn. Likewise, Bertie might end up with Alison, or with Bonnie, or with Claire, or with Dawn. And then Chris could also end up with either of the girls. And David could also be put with any of the girls. So what we have is that altogether there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 possible combinations. And 4 times 4 is 16. Now that principle can be extended up to larger numbers without having to go to the bother of listing all the possible things that could happen. If there are this many people in one group and this many people in another group, and one from each group is going to be randomly selected and they're going to be paired up, all you need to do to find out how many combinations there are is multiply the numbers together, for exactly the reason that we've just shown when we've made an actual list for groups where it's small enough for us to do that. So if, for example, there are 25 people in one class and there's 23 people in another class, and one person is going to be chosen from each class to do a reading in a school assembly, it wouldn't be practical really to list all the possible combinations of who could be partnered with who. There's so many of them, but we don't need to. All we need to do is multiply 25 by 23, and that tells us how many combinations there are. So 25 times 23 is 575 combinations. And I've just done that on my calculator. I'm not so good that I just knew that in my head. I have just put it into my calculator. Thinking about another example, if you were told that in a restaurant there were 5 starters, 10 main courses and 7 desserts, and you were asked in your exam how many combinations of starter, main and dessert there were, again, it wouldn't be practical to list every combination of things that can happen because there's going to be so many of them in this case. But all we do is multiply the numbers. So there's 5 starters, 10 mains and 7 desserts. And if we multiply 5 by 10, we get 50. And if we multiply 50 by 7, we get 350. So there are 350 different ways that someone could choose to have a 3-course meal, which is far too many in an exam to list individually. but we just times the numbers together. So it's nice and easy, really. The only way it changes is if the selections are going to be made from the same pool. So if we're choosing a starter, a main and a dessert, we're choosing 3 items from 3 distinct groups. If we're choosing one person from one class and one person from another class, we're choosing from 2 distinct groups. Sometimes you might be choosing 2 items from one group. So an example of that might be, in a class of 25 people, if you're going to choose 2 people, then when you choose the first person, you've got 25 choices that you could make. But then after that first person has been chosen, now there's only 24 people left to choose from. So the possible combinations are 25 times 24, which equals 600 combinations. But the order doesn't matter. So if you're choosing, say you're choosing Alex and then Bonnie. So say Alex was the first person chosen out of the 25 and Bonnie was the second person chosen out of the 24. You have the same 2 people as you would have had if Bonnie had been chosen out of the 25 and if Alex had been chosen out of the 24. So what we do is we divide the 600 combinations by 2 to eliminate all the combinations that are actually the same but the other way round. So choosing Alex followed by Bonnie is no different than if you choose Bonnie followed by Alex. So we times the numbers together, and then to eliminate all the duplicate combinations, we divide the number by 2, which gives us 300 combinations overall. If, on the other hand, the first person chosen was going to be given a specific role, so perhaps they were going to have to read a poem, and then the second person chosen was going to be given a different role, so perhaps they might have to design a picture, then the order does matter, because Alex reading a poem and Bonnie designing the picture is different than if Bonnie was reading the poem and Alex was designing the picture. So if the order does matter, then you don't divide by 2 because there aren't any duplicate combinations, which can be a little bit tricky to get your head around. So if you're on higher tier GCSE, just put a title of combinations and we'll just summarise those points. So just put summary. If you are picking from separate pools, you just multiply the numbers. If you are picking from one group, but the order does matter, e.g., the first person chosen will have a different role from the second person chosen. You also just multiply the numbers. If you are picking from one group, and the order does not matter, you multiply the numbers and then divide by 2. To eliminate any duplicates. You won't be asked to choose more than 2 from a single group. Where the order does not matter. Okay, and that's the notes part done. Now, you're not always told in the question whether or not you're picking from a single group or 2 groups, and you're not always explicitly told whether the order does matter or doesn't matter. So these questions are very much a case of having to use your logic to decide for yourself, does the order matter? Do I have one group or more than one group? And then you apply the conditions that we've just written about to the question. So if you just put, e.g., in a group of 12 people, 2 are to be chosen at random. The first person chosen will be team captain. And the second will be referee. How many different combinations of team captain and referee are there? And if you want to have a think about it yourself before I show you, then just hit pause, go back to the summary that we've just written and have a look, and then I'll go through it in a sec. So in this case, the order does matter. So we just multiply the numbers. So there's 12 people to start with, and one of them's going to be chosen to be team captain, which leaves 11 people to choose from who might be chosen to be referee. And we just multiply the numbers, and 12 times 11 is 132 combinations. If we do another one, so put, e.g., there are 4 ice cream toppings. Flake, raspberry sauce, sprinkles, and toffee sauce. You are allowed to pick 2 flavours. How many combinations could you choose? Again, if you want to try it for yourself, then hit pause and have a look back at the summary to help you, and I'll go through it in a sec. Now in this case, the order doesn't matter. If you have sprinkles and chocolate sauce and sprinkles, it's the same combination. So the order doesn't matter. To start with, we've got 4 flavours to choose from. When we've used one of them, there's 3 flavours left to choose from, and 4 times 3 is 12 combinations. But the order doesn't matter. So in this case, we need to divide that 12 by 2 to give 6 combinations. And that's just because chocolate sauce and sprinkles is the same really as sprinkles and chocolate sauce. I know some of you might prefer the sprinkles then the sauce, and some of you might prefer the sauce and then the sprinkles, but really it is the same combination. The order doesn't really matter. So we divide by 2 to eliminate all the duplicates. Let's have another example. So I'll put e.g. in a football league, there are 16 teams. On Easter Sunday, each team is to play one other team at the local park. How many combinations are there? If you want to try it for yourself, hit pause. Again, in this one, the order doesn't matter, because if Bradford play Leeds at some ground that isn't either of their home grounds, that's the same difference as if Leeds play Bradford at some ground that is neither of their home grounds. So 16 times 15 equals 240. But to rule out the duplicates, because the order doesn't matter, we divide 240 by 2 to give 120 combinations. If you're going for one of the higher grades, and certainly if you're going for one of the higher grades and you intend to do A-level maths, please write these on 2 separate lines, because mathematically speaking, they're 2 separate sentences. So what I sometimes see people do is say 16 times 15 equals 240, divided by 2 equals 120. But that's not mathematically true, because what you're saying in that sentence is that 16 times 15 is the same as 240 divided by 2 is the same as 120. But 16 times 15 is 240, which is quite obviously not the same as 120. If people are sort of doing foundation, or they're definitely not going for one of the higher tier levels, I let them do this if they absolutely must, so as not to confuse them. But if you are going for one of the higher levels, so a 6+, and if you're wanting to do A-level in particular, then please write it like this as 2 separate lines, because what you're saying is 16 times 15 equals 240, new mathematical sentence, and 240 divided by 2 equals 120. So it's only a little thing, but it is an important thing, especially if you want to go on to do maths at a higher level. Let's do another one. So just put, in a meal deal, there are 5 types of sandwich, 3 types of cake, and 4 types of drink. You are allowed to pick 1 sandwich, 1 cake, and 1 drink. How many combinations are there? If you want to try it, hit pause. And then in this case, you're picking from 3 distinct groups. So there's the sandwiches group, the cakes group, and the drinks group. So it's 3 completely different pools that you're picking from. And there are 5 types of sandwiches, 3 types of cake, and 4 types of drink. So you multiply 5 and 3 and 4 together to give 60 combinations. Let's have one more. So e.g., in a class of 30, 3 people are to be chosen at random. The first one chosen is to be litter monitor for the week. The second chosen will be homework collector for the week. The third chosen will be lunch monitor for the week. How many combinations are there? So if you want to try it for yourself, hit pause and have a go. You will need a calculator for this one. So in this one, you're picking from one group, but the order does matter. So we multiply the numbers 30 times 29 times 28, because when we choose the first one, there's 30 to pick from. Then when we choose the second one, there's only 29. When we choose the third one, there's only 28 left. So we multiply those numbers together, which is 24,360 combinations. And because the order does matter, if we choose Alex to be litter monitor, Sarah to be homework monitor, and David to be whatever the third thing was, that's different than if we choose David to be litter monitor and Alex to be lunchtime monitor or whatever. So the order does matter. Each person chosen is going to have a specific job. So there won't be any duplicates. So we don't need to do any dividing, and that's the final answer. And as far as combinations go, that's about as much as you're tested on at GCSE. So it's only quite a small topic. It's one where you've got to use a bit of logic. It's quite a standalone topic. They sometimes tie it in with a bit of probability, particularly on a foundation paper, but for the most part, it's just a standalone question for 2 marks. So it's not a major topic, and don't worry about it too much if you're not very good at it or if you're running out of time to revise. There's many other more important topics, but this one tied in quite nicely with VE Day related things. If you're only interested in the GCSE content, then feel free to end the video here. But what I'm going to do now is I'm going to look at how those GCSE topics extended right up to the design and creation of the Enigma machine. It gets quite complicated quite quickly, so hold on tight and don't worry if you get lost. I've got my notes here to make sure I don't get lost, so I don't expect you to follow it all thoroughly, but I think you might follow bits of it and hopefully you'll find it interesting. Now, the Enigma machine was designed by a German inventor called Arthur Scherbius. And before we look at how it actually worked, there's 2 things that you need to know. The first thing is that the English alphabet has 26 letters, which I hope you already knew, but in case you didn't, the English alphabet has 26 letters. The other thing you need to know is that in the simplest kind of code, one letter is replaced with another using something called a Caesar shift. So if I have the alphabet, or the first part of it, I'm not writing it all out, and then I have another alphabet that's been moved to one side. Then what would happen here is that every A would be replaced with a D, every B would be replaced with an E, every C with an F, and so on. So by shunting one alphabet sideways under another and then matching up pairs, you have what's called a Caesar shift, where one letter just replaces another directly. So if I was to replace with a Caesar shift all the letters in the word maths, if I was to move each letter up one place, then M would change into N. The next letter after A is B, so A would be replaced with B. T would be replaced with U, H with I, and S with T. So the word maths, if I was to use a 1-letter Caesar shift, would be replaced with N-buet. Now these types of codes are actually really easy to break, because in any language it's usual for some letters to appear more often than other letters. So for example, in English, the letter E appears really frequently. So if you had a coded message that looked like a load of gobbledygook, but the letter Q appeared way more often than Q usually appears in English, then you might reasonably deduce that the Q was representing an E, and you might make that substitution and see what you got. We might also in English look at words with 3 letters and deduce that they either represented the word the or the word and, both of which crop up really frequently. And so clues like letters appearing more frequently or trying the and in 3-letter spaces are often enough to crack Caesar shifts. So although they can look complicated when they're coded, they're actually very easy to break, and it's quite possible for one person to do it just using pen and paper relatively quickly, as long as you have enough words in the message to be able to look for 3-letter words or frequently occurring letters. Now, on an Enigma machine, what happened was you pressed a letter on a keyboard. So you sort of had two keyboards really, one on top of another, and you would press letters on this keyboard here, and other letters would light up on the lamp board. So you'd have a keyboard where you'd do your typing, and you'd have a lamp board where other letters would light up. So if you pressed an A and then a letter R lit up, that would mean that in your message that you were writing, if you were writing anytime now, if you pressed A and R lit up, then you would replace A with R in your message. And then if you pressed N and Q lit up, then you'd replace the N's with Q in your coded message. So you'd press one thing and another thing would light up. If no coding had occurred, then you'd press A and A would light up, and you'd press B and B would light up. But what Scherbius thought of doing was putting the 26 letters of the alphabet on a wheel and using that wheel to create a Caesar shift. So in other words, if you have the letters A to Z running around a wheel, which I'm not going to draw them all, and then you have another wheel also with the letters A to Z, but you make it so that middle wheel can be turned, you have a sort of mechanical way of shifting the alphabet so that different letters match up with those letters. So you have like a wheelie way of making a Caesar shift code. So Scherbius thought of putting a wheel and using that wheel to create a Caesar shift. So now perhaps you'd press A and R would light up, and so on. That would mean that there are 26 possible positions that middle wheel can be put in. So there's 26 different ways that you could turn that middle bit to make pairings with the outside edge, which effectively means that there's 26 different alphabets that you could use for a Caesar shift code. If Scherbius had left it there, all he would have achieved would be a Caesar shift code, and they're really simple to break. So he had an idea that every time a key was pressed, that wheel would turn one place. So for your first letter press, A might be replaced with C, but then for your second letter press, it might need to be replaced with D instead, and then for your third letter press, it might need to be replaced with E instead. So what you'd then get is all 26 different alphabets, different code alphabets, all being used in just one message, because with every single key press on your keyboard, your wheel would turn by one place. So you'd have all 26 different possibilities going on inside one message, which would be obviously more complicated to break. It wasn't complicated enough though, because if you pressed a key 26 times, the wheel would have done a full turn and then it would be back in its start position. So that would allow code breakers to look for patterns every 26 letters, because they would know that every 26 letters the wheel would be back at the original position. So Scherbius decided to introduce a second wheel. So you would press a key on your keyboard, and your first wheel would turn. And then he had an idea to introduce a second wheel. With your lamp board up there. So this one would turn every letter press. And this one would turn every time the first wheel had done one revolution. So now we have 26 times 26 combinations. 26 different alphabets that are sort of in use there, times by another 26 that are in use there, which made 676 different combinations, all going on in one message potentially. That is still not difficult enough to be unbreakable. So he then introduced a third wheel, and that third wheel would only move one place when the second wheel had done one revolution. So your first wheel would move every key press. Your second wheel would move every time the first wheel had done one complete revolution. And your third wheel would only move one place every time the second wheel had done one revolution, which would make 26 times 26 times 26 combinations, which would make 17,576 different combinations, different ways of coding a particular message. The whole machine included a reflection mechanism. So the person sending the coded message would press a letter, and then they would see what letter lit up, and they would replace the letter in the message with whatever had lit up. The recipient of the message would also have an Enigma machine, and they would set their wheels up exactly as the sender had set their wheels up. And that would mean, because of the reflector mechanism, that they would read their coded message, and they would enter the first letter of their coded message into the keyboard, see what letter lit up, and replace the coded letter with whatever had just lit up. And they'd do that for every letter. So they'd write every letter of the coded message on the keyboard, note down every letter that lit up on the lamp board, and little by little, they'd translate their message one letter at a time. In order for that to work, the person sending the message and the person receiving the message had to have agreed in advance a starting position for all the wheels, because if you didn't have a starting position for all the wheels, then there'd be that many possible combinations of arrangements that you might need to try before you hit on the right combination. And the agreed arrangement of wheels was called a key. And the Germans published in advance what key would be used on what day and shared it among all their own staff, so that on any given day, everybody would know how to set up their wheels, whether they were sending a coded message or whether they were receiving one. Obviously, they kept it a secret, because if everybody else knew the key, then they also would be able to translate the messages. So these published keys were top secret and were only distributed among their own troops. But without that code book, without that key, you'd have that many combinations to check. That meant that if one person checked one combination every single minute of the day and night, you would need 2 weeks to check all the combinations, by which time the message might be out of date. That is a lot, but if you employ a dozen staff doing it, it drops down to just 1 day, so it still wasn't complicated enough, and Scherbius needed to make it even more complicated. He could have added some more wheels, but to save on space, what he decided to do was make it so that the 3 wheels could be put in a different order. So you'd choose one wheel and put it in a position, and there were 3 wheels to choose from. Then of the 2 wheels that were left, you'd pick one and put it in the second position. and then there'd only be one wheel left to go in the last position, which meant there were 3 times 2 times 1, which equals 6 combinations that the wheels could be put in. That's like the question where we picked someone to be form captain, someone to be litter monitor, and someone to be dinner monitor. It's like picking from the same pool, but the order does matter. So you don't do any dividing, you just times the numbers together. That is exactly that principle. So now we've got 17,576 alphabets and 6 combinations of wheel, which meant 105,456 combinations, which is better, but still not enough. So this now is where the math starts to get a bit tricky. Scherbius invented something called a plug board for the machine, for the keyboard part. And he made it that before you even got onto the wheels and the pressing, you might swap certain pairs of letters on your keyboard. So you might unplug them, change them around and plug them back in again. I believe you can actually do that with computer keyboards. Even now, I'm sure that there used to be a trick that people played at secondary school where they change the keys around somehow. I could never do it, but I believe that some people did it. So you'd press one letter and a different letter would come up on your computer screen. So he made it that 6 pairs of letters were swapped on his plug board, which amounted to 12 actual letters, because obviously there's 2 letters in each pair. On the basis that there's 26 letters in the alphabet, 6 pairs were swapped, which was 12 actual letters, which meant 14 letters stayed in position. Thinking back to our GCSE combinations, if we're to choose 2 letters from the alphabet to switch places, there's 26 to choose from, and then after we've taken one, there's 25 left. So there are that many combinations of letters to choose from. But because swapping an A and a B leads to the same result as if we'd swapped a B with an A, so if you swap an A and a B, everything's in the same position as if you swap a B and an A. So we need to divide by 2 to eliminate that duplicate combination. And 26 times 25 divided by 2 gives us 325 ways that we can make the first pair. After that, there's 24 letters left to choose from, which can, after we've chosen the next one, there's then 23. So for our second pair, there's 24 and 23 letters to choose from, which for the same reason as there needs to be divided by 2. So that gives us 276 ways of choosing. For our third pair, there's only 22 letters left and 21 letters left. And again, it doesn't matter which order you put your pair in, so we divide by 2. Which gives us 231 combinations. By the time we've come to choose our fourth pair, there's only 20 letters to choose from and 19 letters to choose from, which again needs to be divided by 2, which gives us 190 ways. For our fifth pair, we have 153 ways. I've forgotten what numbers I just wrote on the other page, so I think it might have been 18 and 17. Yeah, I think that's 18 times 17 divided by 2, that one. And then the next one would give 120 ways, which I'm presuming was 16 and 15. But I can't remember what I wrote on that page. But for our fifth pair and our sixth pair, there's 153 ways of choosing and 120 ways of choosing. In maths, and means multiply. I talk about that a lot in probability work, but and means multiply. In the Enigma machine, the first pair was used, and the second pair was used, and the third pair was used, and the fourth pair was used, and the fifth pair was used, and the sixth pair was used. So all the combinations got times together to produce an answer of 722, 820, 898, 8, 0, 0, 0, 0 combinations. I don't even know how to say that number. I could probably work it out, but I don't know how to say it off the top of my head. That is a big number. However, it doesn't matter what order the pairs were actually swapped in. So if we swapped A and B, and we swapped C and D, and we swapped E and F, and we swapped G and H, and I and J, 1, 2, 3, 4, 5, and we swapped K and L. So if 6 pairs changed positions, it doesn't matter what order they're written in. That's the same lot of things being swapped as if we swapped C with D, and then we swapped K with L, and then we swapped A with B, and so on. So if we do all our 6 swaps, our keyboard will look exactly the same as if we do the same 6 swaps in a different order. The net result will be the same. There are 6 times 5 times 4 times 3 times 2 times 1 ways of listing 6 different objects. So we could write that list in that many different orders. All those numbers times together equal 720. So there's 720 different ways that those 6 numbers can be arranged, which is a lot for 6 numbers. You wouldn't think it would be that much, would you? But it is, which means that this number here can be divided by 720, which produces an answer of 100391791500 overall combinations of plug board. So this is all just about the plug board part of the Enigma machine. And the reason I've divided is the same as in our GCSE questions. So if we have 25 people in a class and 2 of them are going to be chosen to give a presentation, choosing Alex and Bonnie was the same as choosing Bonnie and Alex, provided they weren't both going to be given different roles. So the reason we do that divide is to just eliminate all the duplicate ways of listing those 6 things. So we have 17,576 positions that the 3 wheels can be in. We have 6 ways of actually arranging those 3 wheels inside the Enigma machine, because remember, he made it so the wheels could be taken out and replaced in separate orders. So that's to do with how far the wheels have actually turned. That's to do with what order we've actually put the wheels in the machine in. And this number here is the number of different ways that the plug board can be arranged, with the 6 pair swaps and the 14 letters being left in place. That's our plug board, that's our wheels, that's the position of our wheels. Multiplying those together, because they're 3 separate groups, so 3 separate pools of things, if we multiply those together, that gives an overall answer of 1058691,676, and then that's as many digits as my calculator would show. So it put it in something called standard form after that. So I'm filling in these with zeros now. So 1, 2, 3, 3, 6, 7. That number. So there are that many different possible start positions for the Enigma machine to be in, using the different combinations of wheels, the order of the wheels, and plug boards. That is a big number. It's so big I don't even know what the number is. It's big. I think I read somewhere it was over 100 billion. But yeah, I don't know how to actually say that number. It's so large. And without knowing the start position of the Enigma machine, that is how many possibilities there might have been for what the start position was. So if you just got a randomly coded message that had come from an Enigma machine and you didn't have the key, you might have to check up to that many possible combinations to find the correct arrangement. If you were able to check a combination every single minute, it would take longer than the age of the universe to check all those combinations. That is how difficult it was to crack the Enigma machine. Now, talking about how the Enigma machine was actually cracked would take ages, and it would be way too advanced really for me, if not you. So I'm not going to cover how it was actually cracked. But believe it or not, it was in the 1930s by a Polish mathematician and his team. He was called Hodges, and he did devise a method of cracking it. So before the Second World War, the Germans had to actually make that even more complicated by introducing 2 extra scrambler wheels to the machine. And it's that version of the machine that Alan Turing and his team worked on in the Second World War at Bletchley Park. I hope you found that interesting. If you are interested in that or in knowing more about codes, I took a lot of this from the code book by Singh. So he's written a whole book about codes, not just the Enigma, but codes that came earlier, codes that came later. So if you do want to know more, then that's quite a good book to read. The work that Alan Turing and his team did at Bletchley Park was really responsible for the invention of modern computing. So it was very significant, but because it was also very secret, none of the personnel really got the recognition that they deserved for all of the work that they did. And in fact, Alan Turing died before any of his good work was ever known about. It's quite a sad story, really. All right, I hope you found that interesting. Thank you very much for watching, and I will see you in the next one. Bye.